Okay, so we're off Monday and Tuesday of next week. Our second exam is going to be a week from Friday. So let me throw this out here. You can yell now if there's a thing. I sent around an email, but I was thinking to do a review session again the same way as before, like next Wednesday at 6 o'clock. Let me know if that didn't fit your schedule. I'll try to send an email around after class about it. And remember, if you haven't done the first assessment, there'll be another assessment after the second exam. If you haven't done that, you've got until the exam next week to do it. So don't wait till Friday morning. That's a bad idea. Okay, any questions before we get started? All right. So the last time we looked at this example. We looked at the ring of 2 by 2 matrices over the reals. This is not commutative. But has identity. You'll probably remember this old friend from linear algebra, right? That's a 2 by 2 identity matrix. It's one you can multiply any matrix by and it leaves it alone. All right? The units of these are just the invertible matrices. They're the one that you can multiply something by and get the identity matrix. And if you remember, these were the matrices that have determinant not zero, right? And the zero risers. The language you probably heard when you were in linear algebra, the singular matrices. It's a set of matrices. Right. So let me give you a quick thing here. Composition. But R has an identity. Then if R has an identity, then the set of units is actually a group under multiplication, right? Let me sketch this. Then this such that B1, B1, and B2, B2, B2. Notice 2 units is still in there because if you multiply U1, U2 by V1, V2, and also on the other side, let me be careful. Because these collapse to 1 and then the outer ones collapse to 1. So the product of 2 units is a unit. That's good. Multiplication is associative in R. So we know it's associative with this group. There's the identity, and by definition, if U is a unit, then U unit. Okay. Let me give you another quick proposition that I won't prove, and the reason is you'll see it's in your homework. Proposition 918. And suppose that U is in UR. And X, Y, notice so if there's a power of X that's 0 and a power of Y that's 0, there's a power of X plus Y that's 0. That's cool. XY is nilpotent, and E plus X is infinity. These are all homework exercises. Let me point out in your homework, you should see that you honest to goodness need community here. If you want counterexamples, look at 2 by 2 matrices and look around with it a little bit, and you'll be able to find something. Let me also point out that the only reason you ever need 1 is for the statement of the unit. Anytime you talk about units, you have to have a 1 by definition. So 1 and 2 are still true, even if you don't have an identity. Okay. Any questions? All right, so let me throw a definition at you. Definition. But on the green, such that R minus 0 is a group under 1. Or equivalently, the units are minus. These are 2 equivalent statements. Another way to put this is every element that's not 0 is a unit. We call R a dictionary. Why is that? Because basically what that means is you can divide by any non-zero element and stay in there, right? So let me kind of give you a little trend set of an example. And that's what we call a division ring, because you can divide B by A in certain sense, right? Because since A is not zero, A inverse is in the ring, right? And so A inverse times B is in the ring. That's why it's called a division. If you have a division ring where multiplication is commutative, we call that a field. By the way, I'm curious, how many of you have heard the terminology field before?
I heard it in analysis.
Oh, where did you say you heard it before?
Analysis?
Analysis. Another place you might have heard it is linear algebra, right? Because you have a vector space over a field. Has anybody said that? I don't know what your linear algebra class was. Did you always do linear algebra over R, or did it sometimes talk about a more general field, like reading complex numbers or rational numbers or something like this? Right. So let me give you some fields first. Ooh, that's one of my favorites. Because if you have any non-zero rational number, A over B, you can turn it upside down. B over A is still a rational number. Everybody agree with that? Here's another one. R. Complex numbers. Anybody think of a field is finite? All these are infinite fields.
Z5?
Actually, that's exactly what I was thinking. Z5 is actually. In fact, more generally, ZP or P is prime. Let me demonstrate for Z5 just for fun, because it's always good to have fun class. So why is Z5 a field? Well, we know that Z5 is a ring, right? We played around with this a little bit. And we looked at the figure at Z6, and we had in Z6 was weird, right? Because 2 bar times 3 bar with 6 bar, which is 0. I can multiply two non-zero things, it's 0. What I have to convince you that this is a field, I need to convince you that every non-zero element has an inverse. 1 is its own inverse, because 1 times 1 is 1. And 4 is its own inverse, because 4 times 4 is 16, and mod 5, that's 1. And 2 and 3 are inverses of each other. Because 2 times 3 is 6, which is 1, you can see mod 5. So this is an example of the field. It's basically the same game for any prime. Any non-zero element is a field. So there are finite fields. So if look at our example, we went from very big, like complex numbers, to very small, C mod P. Let me go one more step. Can anybody name, so there's a bunch of fields, can anybody give an example of a division ring that is not a field? That's a little harder, actually. I'll let you ponder this example, but I'll let you ponder both of them and let me know if you had trouble with it. But here's one way that you can go. Okay, so what I mean by this notation is I am going to take rational functions in two polynomial variables, x and y, just like you were in Calc 3, right? Rational functions. So you saw stuff in Calc 3 where you had to take like partial derivatives and crazy crap, probably made you cuss and everything else. But you'd have like functions like x divided by x squared plus y squared, things like this. But I'm not going to assume variables can be. So when you see x, y, and you see y, x, they're two different things. Right? And so, actually, this is a good example of a division ring that's not a field. Here's another example, quaternions. Well, so let me write out the way I did. And I-K, so this here should be named like that. That's one way to do it. Where this is the quaternions, right? These contain the complex numbers. If you let C and D be 0, then these are just ordinary complex numbers. These relations ought to look familiar because this is the quaternion group of order A, right? You've got I, well, you've got plus or minus I, plus or minus J, plus or minus K, so that's 6, and then plus or minus 1, right? So the fact that these don't commute make this behave strangely, right? So for example, times, what would this be? This would be I squared plus IK plus JI plus JK. If I use the associative property, I squared, IK, JI, JK, the distributive property, I should say. This is minus 1. Let me see if I can, this is minus J. This is minus K. And this is I. I bet if we try them in the other order, we'll get something different. Let me see. Let's fix this up a little bit.
Is that H bar? Just like let H.
Yeah, that's supposed to be a fancy capital H. Sometimes it's called a half. This is called a quaternions, but sometimes they use an H on it. Physicists like to use H. If you give us the other order, I squared plus IJ plus KI plus KJ, right, which is going to be -1. IJ is K, and I already know it's different, but anyway, KI, so what's KI? KI should be J, and KJ should be minus I. And notice this is something different, the J and the K sign, actually all the IJ and K should change the sign.
On that one, the I squared is negative.
Oh, because I wrote this all down wrong. I'm sorry. This is not all wrong. This is -1, right? I squared should be -1, not 1.
And then whenever it's IJ, it's positive, and JI when it's flipped is negative.
Yeah, so for example, if IJ is K, then when you flip the order around, it's the opposite sign. And that's actually, I'll prove that to you. So for example, if ij is k, then ij is ki. This is what I'm trying to do. I'm trying to do ji. So let's walk on this side. Ij equals k, so ij is what, ki. I'm trying to get ji, so I'm going to multiply by minus I on this side. Then let's see, ik is minus j. Oh, so ki should be j. And then, so it's the opposite sign. Anyway, it turns out that this thing is, in fact, it's not commutative. And if you're patient, you can show that everything that's not zero actually has an inverse. So this is an example of a division ring. It is not a field because the multiplication is not commutative. Okay. Let me give you another definition. Okay, I'm going to define a very important class of rings called integral domains. I put integral in parentheses because as we get more familiar with this, I'll get lazy later and just call it a domain. So if I ever say a domain, that is short for an integral domain. What is one of these animals? It's got to have all this. Commutative ring with one. It's got to have an identity. Has to have an identity. And no non-zero zero drivers. Okay, an integral domain, commutative ring, identity, and no non-zero zero drivers. So what that means is integral domain has one and here's why integral domain should be your safe little happy place. Integral domains are where you have the old familiar multiplication. If the product of two things is zero, then one of those things has to be a zero. An example of something that's not an integral domain would be z mod 6, because we saw that 2 bar times 3 bar is 0 bar, and neither one of those is 0. Not an integral domain. However, the ordinary integers is an integral domain. Any place where you can say, when I multiply two things and I get 0, one of those things has to be 0, that's an integral domain. So if you think of a ring where a place where you can do addition and multiplication, integral domains are the best place to be. Because whenever you get this equation, you can deduce the one of the factors of 0. There's another class of integral domains that are important. And again, fields are important as far as rings go because, like I said, you've seen them in Well, it's on an analysis. You'll certainly see them in analysis. You see them in for advanced calculus. You see them in linear algebra. Any field, you have this going on. The proof of this is pretty easy. Okay, suppose you have a field. Let's go through my integral domain checklist. Commutative. Check. Any field is commutative by definition. Has identity. Check. Any field has an identity because the non-zero elements are group by multiplication. And finally, suppose that you have the product of two things in the field being zero. We want to prove that one of those things has to be zero. Well, let's see if we can get. Now suppose because if A is zero, then we're done. So let's suppose that A is not zero. Here's what I'm going to do. I'm going to multiply on the left, although it doesn't matter because the ring is commutative, by A inverse. And so I get A inverse A. And there we go. If A is not zero, B must be. So any field is an integral domain. Here's another good thing. Okay, any questions? Integral domains. Here's kind of a nice corollary to the fact that the product of two things being zero means one of them has to be zero. Integral domains have what we call the cancellation problem. You can do this. So, in fact, I'm going to state this more generally than for integral domains. This is about solving equations. Proposition 9, 13. Suppose R is yeah, say that. Suppose R is a ring. I won't even see with no non-zero, zero classes. Then, if A, B equals AC, and A is not zero, then and perhaps you guys can see why this is called a cancellation problem, right? I can remember back, when I was first taking algebra, and I mean like high school algebra, oftentimes the teacher would write something like this, and then they'd put little lines in there and cancel out the A's, right? Well, if you're in a ring with no non-zero zero divisors, you can do that. Um, so suppose AB equals AC, and so AB minus AC is 0. Now, by the distributive property, I can pull that A out. Now, since A is not 0 and R has no zero divisors, non-zero, zero divisors, you must have that B minus C is 0. Because this 0, and this ain't 0, and since there's no zero divisors, this must be 0. And so I get B equals C at once. By the way, I didn't say anything about the ring B commute, and I didn't use that. Can anybody tell me how I might generalize this theorem? I didn't state it as generally as I could. Anybody got how any? Well, what did I really need to do this proof? Did I really need that this has no zero divisors? I mean, that's the crucial step, isn't it? This is 0, this is not 0, and there's no zero divisors. How could I state this more generally in the case where the ring may not be commuted? Any ideas?
Can you multiply by inverse of
I'm sorry, multiply
A?
by.
Multiply by inverse of A.
Oh, well, yeah, actually, that's a great idea, but see, here's the problem. A may not have an inverse, actually, in the ring, right? That's kind of problematic, right? Because actually, so you asked a very good question, actually. Let's say that this equation takes place over the integers, right? We all know that you can cancel the 2, right? And get x equals 1, and so the b not, right? And what you suggest is multiply by the inverse, and that's another way to do that. But you can't do that within the ring Z, because 2 has no inverse that is an integer, right? Its inverse is a rational number. So yes, you can multiply this by the inverse if there's some bigger ring that contains this where there's A inverse in there, right? But we want to try to stay in here if we can. I make this statement and I say, since A is not 0 and R has no non-zero zero divisors, I don't really need that. I only need for R to not have any left zero divisors to make this statement, right? So in the non-commutative case, there might be 2 parts of this theorem. If AB equals AC and there are no left zero divisors, then B equals C. And I could have another statement. If BA equals CA and there's no right zero divisors, then B equals C. This is why, so you can always do things a little bit more generally in the non-commutative case. I'm going to probably concentrate more on commutative stuff so as to not totally bog us down. But everybody see that? Not bog us down even more. So let me give you this is actually one of my favorite little theorems to prove. And you guys will probably sort of catch on to this because there are similar elements to the proof of this as to some things that you've already seen before. I think I made this statement to you all last time when we did that example with Z mod 36. If you remember toward the last lecture, we did Z mod 36, and I said, hey, let's find the units. And we found the units, and we convinced ourselves that the units were everything were relatively right to 36. And then I said, okay, let's find the zero divisors. We convinced ourselves that the zero divisors were everything that had a factor in common with 36. And that sucked up everything. And so everything in that particular example was either a zero divisor or a unit. Here's a more general statement. I'm 114. Let R be a finite community ring. Is an element of R. A is and just so that we're not pathological here, I'm going to say that R is a finite ring that has more than just zero. Here is the stupidest ring in the world, zero. Zero is a ring because zero is an ability group, it's just the identity, and multiplication, it's boring. We're going to assume, because the definitions kind of collapse to the same thing and they're vacuous or zero. Let's just suppose we have a finite ring that actually has more than just the zero in it. Then any element in that ring is either a unit or a zero divisor. By the way, let me ask you all something. Does anybody want to criticize my statement of the theorem? There might be something that occurs to you that it seems like, hey, it looks like Jim may have left something out. Does it look like I left out anything?
Something to a notebook.
Well, yeah, actually, it's going to turn out that. What do you need? Let's see, it's either a unit or a zero divisor. If you've got a unit ring, what do you need?
Oh, not there.
You need an identity, right? And so it looks like Jim forgot to say, oh, an identity. I don't need to say it. This is actually one of the interesting things about this theorem is if R consists all of zero divisors, then you're done. And if there's anything that's not a zero divisor, you get an identity automatically, right? And we'll see where that comes from. So, actually, we'll show that as we go along in developing this, we will show that it actually spontaneously gets an identity. Free. Yeah, every element R is a zero divisor. We're done. So, assume there exists X in such that X is not. And let me emphasize that X itself is not zero, right? Because the ring is not zero, so that X is a non-zero element necessarily. So, in the case that the ring is nothing but zero divisors already, then we can go home. We're done with the proof. So, we're assuming that there's some non-zero element that's not a zero divisor, and we're going to use that. We're going to show this is our strategy. And this is kind of a bold statement that I made here because I haven't even asserted yet that X has an identity. Like I said, it's going to come up along the way. There are actually elements of this that are quite similar to what you've seen when we first looked at groups. Consider the following set. X squared. this, I'm infinite with this, but yeah, it's fine. Let me clarify what I mean by this. X squared, x cubed, x four forever, that's an infinite list, never stops. However, these are all in the ring R, which is fine. And I don't know much, but I know that any subset of a finite set is fine. Everybody agree with that? So the list must have repetition. How do you spell repetition? It's got it. Right? So there exists, let's say, M. Well, I ain't gonna do this. So there are just two natural numbers, n strictly less than n, such that everybody okay with that? What are you tempted to do at this point? You know what, I'm tempted to cancel that x to the m, aren't you? Just cancel the heck out of that. And then x to the n minus m is the identity. But I can't do that. So tell me what the flaw is in this step. The flaw at this point. You got 31? Why can't I just cancel?
You don't know if there's a multiplicative inverse.
You don't, well, you can actually use a proposition now. So let me take one more step. So I agree. I agree. But you got to be careful here. I think that for sure works, right? Because n minus m is positive, right? So that's a positive power of x. Positive power of x equals, and this should be x to the n. Okay. There we go. Now it works. Right. And so I'm tempted. Right. So what I'm doing is I take this x to the n and I'm pull this out. So let me rewrite this here. This is x to the n. This is x to the n. X to the n minus m. Oh, right. And now I'm tempted to cancel this. Oh, right. Why can't I? Why can't I do it? Right? Because I mean, we just had this result that I could cancel, right? Why can't I do this? Why is the step flawed? That's I didn't assume that there's an identity, so there's nothing to cancel that out. Problem. But I can get around this by doing this. I'll pull out everything that I can, right? Let me pull out x to the n minus 1. Now, x is not a zero divisor. So neither is x to the n minus 1. Because if you can hit x to the n minus 1 by something and have it be 0, then you're hitting x by something and have it be 0. Therefore, everybody agree with that? Now, I'm going to make a quick claim here. I claim that x to the n minus m is the identity. So what I have to do is I have to show that this function is like an identity. And to this end, consider to see this. That y, anything in R, and look at y times that's equal to yx, because we just proved that x to the n minus n minus plus 1 is the same thing as x. So I can replace that by x, which means that y so now I have y x to the n minus n plus 1 plus yx equals 0. Now I've got this y here, so I can pull x out. So if I pull an x out, I get y x to the n minus m minus y equals 0. X is not a zero divisor. So y x to the n minus m equals 1. Also, if you do this on the other side, you get x to the n minus m y equals y. And so that's it, folks. Because now, what do we know? We know that x to the n minus m is the identity of R. Right? Because it leaves y alone on both sides. Therefore, x times x to the n minus m minus 1 equals 1R. And so minus n is positive, so this is at least 0. That's a positive power base. Well, a non-negative power base. Okay, any questions on that? Any questions? Okay, well, I will be back in my office in just 5 minutes, hopefully. Any questions? And I'll trust Wednesday thing. Other than that, you guys stay safe, and we will see you by Wednesday.